Thanks. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this afternoon. Thank you for these students. I just pray that you'd help us use this time wisely just to learn a little bit more about your creation, Lord. In your name I pray. Amen. I will close the door, I suppose. Thanks. Okay, so we have most of the necessary ingredients to start working problems in here, so I'm going to do that. So these problems will be very suspiciously like your homework. That's not too offensive to you guys. So here's an example. You have a hockey puck with mass 0.16 kilograms at rest at the origin on a horizontal frictionless surface of a rink. At time t equals 0, a player applies a force of 0.55 newtons to the puck, parallel to the x-axis. All right. And he continues to apply this force. So this is applied from t equals to what? 1.7 seconds. All right. So then the question is, what are the position and speed of the puck at 1.7 seconds? And then the question is, if the same force is applied again at t equals 5 seconds, what are the position and speed of the puck at 7 seconds? I'm going to leave part B to you guys. I'm just going to do part A. Okay, so if we can do part A, we should be able to do part B. So then the question again is, so that's the given data. The question is, what's x of 1.7 and what's the velocity at time 1.7? All right. It's pretty simple. What we want to do is set up Newton's second law. Newton's second law says what? Force equals mass times acceleration. Very good. So F equals ma. In this case, that's 0.55 is equal to 0.16 times a. So therefore, we have a constant acceleration of 0.55 divided by 0.16. The units that I'm omitting up to this point are meters per second squared, right? Which is what? How many? What's the whatever that is? Yeah. So you said 3.4375. All right, very good. And then what? So okay, now it's a problem of kinematics. So I've got the acceleration. We can take where it's originally at time equal to 0 to be x equals to 0 for our convenience. And we're off to the races. So v at time t is, and it's at rest to start with, right? The initial velocity is 0. Now in part B, that won't be the case anymore, right? For part B, your initial velocity will be whatever, well, you'll have to figure that out. But v of t would be 3.4375. I mean, I'll put the times t, right? So, and x of t will be 1/2 of 3.4375 times t squared. So all you got to do is plug in. This is using the kinematic equations with the initial position and the initial velocity 0. So then we just have to plug in 1.7 and 1.7. What do we get? We get 4.97 for the position, roughly speaking, meters. And the velocity Sometimes they do some significant figure stuff to mess with the answer. I don't know. What I get in terms of raw numbers is 5.84375. But what WebAssign is looking for there is 5.84. So that's WebAssign's happy with that. I assume that we've cut off some digits from the other one. Yep.
Does WebAssign have like a buffer of like 25 or something like that? How accurate is it?
I don't know. Different for different problems. So that's that problem. Let's look at another example, unless there's a question about this one. This is pretty cut and dried, this kind of problem. You have a force, you find the acceleration, and then you're back to the stuff we did before. This is a different concept, which is the concept of weight versus mass. So what's the difference between weight and mass?
One is absolute.
Right.
One is dependent upon the force of gravitation.
Exactly. So you can lose weight by travel. Losing mass is harder. So weight, right, is your mass. Mass times g is the weight. So here, this could be g of wherever. Whereas mass is, as you said, absolute. It's an intrinsic characteristic of a given object. All right. So this problem is hypothetical, something about Jupiter's moon Io. So Jupiter's moon apparently has a gravity of 1.81 meters per second squared. I really disagree with this statement g is equal to 1.81. For me, g is a fixed constant. I do not use g as a variable. G for me is reserved notation. It means 9.8 meters per second squared. I object to this usage of g. Urgh. I fixed it by adding a little sub io. There you go. So here's the deal. We're given that a watermelon weighs 50 newtons on Earth. The question is, what's its mass on Earth, and what's its mass and weight on Io? So you got a watermelon. Uh, 50 newtons, weighs 50 newtons. So let's see here. That's equal to mass times g, where g, of course, means 9.8 meters per second squared. On Earth, that's what g is. Urgh. So what's this say about m? 50 newtons divided by 9.8 meters per second squared. What is that? Let me care about units here for a second. This is 50 kilogram meter per second squared divided by 9.8 meters per second squared. So you see the units work out, right? Meters per second squared cancel, and we're just left with 50 over 9.8 kilograms, which gives me 5.102 kilograms. There you go. There's the mass. That last digit's probably not significant. What's its mass on Io? That's its mass on Earth. It's a stupid question to ask, isn't it? But kind of the point is, all right, folks, mass is the same on Earth and Io. Okay, so this question is very preachy. It's like, you will learn mass is the same on Earth and Io. We will learn it to you. I mean, we'll make you learn it. Yes?
Do we use mass? Do we use Earth as the standard?
Well, if you're given...
Divided by G
Because you're given the weight of the melon on Earth. It's the problem statement. You could be given the weight of the watermelon on Io, and then you'd have to divide by 1.81 to figure out the, the mass. Now, okay, so how do we figure out the weight on Io? What do we do? So it's the mass times 1.81, yeah. Which is 5.102 kilograms times 1.81 meters per second squared, which gives me newtons, and what number? Yeah, 9.23. Does that make sense? That this number would be smaller? $50 newtons on Earth, 9.23 newtons on Io. Of course, it makes sense because the gravitational acceleration on Io is smaller. Because Io is smaller, so it doesn't have as much gravitational pull. You can also check that the ratio of 50 divided by 9.3 is the same as 9.8 divided by 1.8, right? So you could think about these things in terms of proportions as well if you wanted to. Yes, sir?
So the fact that like mass and weight are different, does that mean that like saying how much we weigh is like not something that would be correct?
Yeah, I mean, communicating your mass in terms of weight, it would only make sense if we were always on the same gravitational body at about the same altitude. So, I mean, since we never leave the surface of the Earth, it's only ambiguous for astronauts, right? Or who else? Mountain climbers. There is a slight difference in gravitational acceleration, different places on Earth. I mean, but yeah, whatever. The Earth is actually an oblate spheroid, so it's not quite the same. Oh, I mean, just mountains also, like you guys were telling me a second ago. All right, next example. We have a 4 kilogram bucket of water accelerated upward by a cord of negligible mass. Here's the cord. Here's your bucket of water. All right. The bucket of water has mass of 4.2 kilograms. Bucket of water. The cord, the rope, doesn't have much mass, but this breaks at 80 newtons. So if you put more than 80 newtons on that thing, it's going to snap. The question then is to find the maximum upward acceleration that can be given the bucket without breaking the cord. All right. So this is our first example that deals with tension. Right? Tension is a force that's applied through a rope or cable or something. So if I'm drawing a free body diagram here, I do it on the mass, which is this, right? And so if you look at that, there are really two things going on. You've got this tension force going up, right? What's the other force at play here? Gravity, right? And so that's mg goes like this. Are these equal? What's that? Yes? No. In fact, they are not equal. They would be equal if what? Yeah, if it was moving at constant velocity, or if it was in equilibrium, just static equilibrium, they'd be equal. But if they're not equal, I mean, these aren't equal. The question is what upward acceleration, right, is necessary for this to break. So what we have is ma. I'll take upward. So you guys, you got choices. You can either make up positive or down positive. What do you want me to do? Up. Yep. Okay.
I'm confused about the question. Like, if it's hanging out from a cord, how is upward acceleration going to break it?
If you go to give your yo-yo to Superman and he does this to it, your string will break because he pulls the cord so hard that it breaks the string, because the string just can't pull the mass fast. The string cannot basically transfer the force of Superman's hand to the yo-yo to pull it up.
So it's the top of the string that's moving up then?
Yeah.
Oh, yeah.
Mhm.
That was the bucket.
Yes. We assume the string doesn't stretch. So you could.
I was thinking you were like pushing the bucket from underneath and then shoving
No,
it
we're
up.
pulling. You're pulling on the string. I mean, that's. So MA is equal to. So if we're taking up to be the positive direction, we have T, like this, and then minus mg, given my choice of upward being positive, right? And how do you find the maximum acceleration? Well, you assume that the tension is 80. And there you go. So we got 4.2 times A is equal to 80 minus 4.2 times 9.8. And there you have it. A is equal to, how do you go? Oh yeah, 80 minus 4.2 times 9.8 divided by 4.2, and that's the maximum acceleration upward that is possible. On the other extreme, it could be that the rope isn't even strong enough to oppose the force of gravity, right? It's conceivable that, I don't know if this is some yarn you got from your grandmother, and this bucket has like 1,000 kilograms of water in it, and you try to do this, well, the string's going to break, right? I mean, oh, what? Hey, this is actually not a calculator. I mean, it has a calculator in it, but it would seem more efficient to use this. Let's see here. 80 minus 4.2 times 9.8 divided by 4.2. So I get 9.25 meters per second squared when I put the units back in. You'll forgive me if I am a little bit cavalier about the units in here. You should understand I can do this because I understand units. And if I was a better teacher, I would always write all of the units out on everything and clutter the board with this sea of unnecessary units. And yet I don't. So there it is. Oh, let me check my answer. Okay, yes. It has 9.25 over here. Good. I was worried for a second there.
Professor,
Yes, sir.
let's say we did have to test if it broke. Maybe we knew it broke at, say, I don't know, 1 Newton,
Uh-huh.
and we tried it. Would the acceleration, because of the problem, be negative, even though it break at the force of gravity?
Well, if it's at 1 Newton, say 4.2 times 9.8 is what? So this bucket of water weighs 41.16 newtons.
So
This problem ceases meaning if the string if the string breaks anything, if it doesn't at least hold like 41.16 newtons, this problem doesn't have meaning. The string's not holding the bucket up. I can't say anything. The bucket would just be in free fall.
would the acceleration come out negative if you didn't concentrate?
I mean, the acceleration would be 9.8 meters per second squared downward. It's in free fall. There's no tension.
Is that calculated?
No, you can't pull a rope. I can't.
I understand the problem.
Yes, you're right. So if the tension force is less than the force of gravity, yes, I could still have it falling, and yet have a force upward. That's true. Absolutely. For example, if the tension was 20 newtons, right, and the string is dropping, it would be accelerating at less than g, but it would still be falling down. That's possible. Certainly. Like an elevator where the brake is failing, but it's still slowing it down a little bit, right? The cable's keeping the elevator from free fall, but it's still falling. That's possible, of course. Yeah. That is true. Next example. I don't like this example. I'm going to do a different one. Kind of equivalent, but different. We did some pulling. Now I'm going to do some pushing. So, so here's an example. You're pushing with a force F, all right, on a box of mass M1, all right. There's another box of mass M2 over here. Then the question is, what's the acceleration of this system? And what's the contact force between the boxes? All right. This actually brings into bear another of Newton's laws I haven't talked about yet, which is Newton's third law. Contact force. What's the contact force?
Force transfer between two objects.
Right. So, like, for example, now, here. I'm pushing on this chair, and this chair is pushing on that chair. That's a contact force. Of course, that chair won't move unless this chair pushes on that chair, right? My demo has a certain thing that's not present in our current example. Friction, yes, as you can hear. All right, so, but here's the thing. This contact force, we often use a C for. On the one hand, it goes like this, right? This is the contact force of M1 pushing on M2, right? We can call this C. Well, you know what? There's the same force at this interface the opposite way, minus C, all right? This is the green one is the force of M2 pushing back on M1. This is a third law pair. They come in equal and opposite directions, all right? So this is what Newton's third law says, what is every action, there's an equal and opposite reaction. That's this. Okay, so to solve this problem, by the way, we don't need numbers. I mean, I could put numbers in, but that really would just distract from the point here. I have two masses, right? Now, they're stuck together. They're moving on this frictionless, again, this is like an ice rink or something. But it's a hypothetical ice rink, no friction. Actual ice rinks do have some friction, just not a lot compared to other things we're familiar with. So again, the question is, what's the acceleration of the system? What's the contact force? All right, and I'll leave it at that, okay? My questions. The acceleration and the contact force are what? Acceleration of what? Why is that unambiguous? Is it the acceleration of M2? Is it the acceleration of M1? Which acceleration of what? The first one? Some of you say the first one, some of you say the second one. You should really say it doesn't matter. They're stuck together, moving along the ice. That means they have the same velocity and same acceleration. They have different positions, but the velocity and acceleration are common. So it's unambiguous just to say what's A. Okay. But that said, I can do Newton's law, Newton's second law, 2 times. First time, M1 A is equal to what? By the way, I can neglect vertical stuff right now because there's no friction. What's called the normal force doesn't come into play yet. In a minute or two, I'll redo this problem taking friction into account. All right? So M1A is equal to what? It's equal to, what are the forces on M1? right? So you have just decided that A is positive if it's going to the right by saying, and I guess I can agree with that, minus C, right? Over here, here's a picture of what's going on. We have the force this way, and we have the contact force that way, right? You could put a minus C if you like it, whatever. Anyway, so that's the picture, M1. How about M2? We can also apply Newton's second law to M2. M2, what's the force on M2? C. Yep, and that's it. See, this force is not applied to M2 directly. In the consideration of these free body diagrams, we only think about the forces which are actually on the object. So that's a very freeing thought. Now what happens? Right, if we add these equations, what do we get? M1 plus M2 times A is equal to F, right? So therefore, the acceleration is the force divided by the total mass. It's as if these two things are stuck together to just make one big particle with total mass M1 plus M2. Some of you, as soon as I wrote this problem down and you finished understanding what I was saying, immediately knew from your intuition that that's what the acceleration was, right? There's some subset of you who think this way, and that's fine, right? But you should understand that's a derived consequence of applying Newton's second law to both objects separately. For those of you who understood what I just boxed in intuitively, I wonder, could you have told me what the contact force is? Maybe, maybe not. What is the contact force? M2A, right? M2 times F divided by M1 plus M2. As a quick check, what happens when they're equal, M1 and M2? C is, yeah, the contact force is a half of F, right? And you can think about other kind of limiting cases. As M1 gets really big and M2 gets very small, the contact force on M2 gets smaller and smaller and smaller, and vice versa, right? Like, if you take a sheet of paper and then you put a Mack truck on the other side of it, right? And then you put a force on the piece of paper to push the Mack truck. The force you push on the paper and the force that the paper then pushes on the Mack truck, about the same. Let's say instead of a piece of paper, let's say a sheet of tin or something. So whatever caveat you're thinking about is gone. It's an adamantium, a thin sheet of adamantium. It can't be flexed or blah, 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 blah. I like to think about this. I like to think about the continuous analog of this. What if I think about a loaf of bread, or maybe a loaf of aluminum, and what if I apply a force like this here, and then I think about chopping this block of aluminum up into pieces. Then I can ask, if I look at any particular like slice, I can ask what's the contact force one way or the other. So like the contact force would be greatest at the point of application of the force, and then if you think about the slices all the way at the other end, it drops to 0. Don't worry, I haven't figured out a way to work this into a problem yet. Let's see here. You can do this with 3 boxes just the same, right? Then you have 2 contact forces, and it's more fun. I put that on tests in past years. You'll find it somewhere. It's one of my favorite problems. This or versions of this. I like the complete lack of numbers. Just got letters. I like letters. Okay, I digress. Next problem. let's see here, I will do something like number, well, do number 8. This is basically number 8 of homework 4, roughly speaking. You got 2 horses, all right, and they're pulling on a stump. And you got one pulling this way, and you've got another one pulling this way. This is F2. This is F1. And you're told that, so altogether, these 2 forces, there's a rope. These are ropes, right? So you maybe there's a, I don't know how to, 2 horses are pulling on these ropes, and they're putting a tension force in each rope that creates a force F1 this way and creates a force F2 that way. And this picture is, I'm trying to draw 3-dimensional. If I was to draw it straight down, it would look like this. Here's the stump, here's the rope, here's the other rope. This is F1. So here's like a top-down view. Here's F2, like that. All right?
Do you assume that forces are perpendicular to each other?
Well, that's also given. What? Excuse me. Wait a minute. We're given that the resultant force has a magnitude equal to that of F1 and makes an angle of 90 degrees with F1. We are not. So no, we are not given. In fact, we are not given that these are perpendicular. So my picture, you're correct. My picture is a little bit askew. So I don't know. Actually, I don't know exactly what this looks like. But I do know that the resultant force it makes a right angle with this one. So the resultant force, of course, would be what? The resultant force is F1 plus F2, okay? So the sum of the forces, the resultant force, makes an angle of 90 degrees with F1. All right. What else are we given in this problem? All right. I got to bail on my current picture because it's not helpful. I mean, it's not wrong. It's just not ideal, the picture I drew. I'll put a better one up here. We're asked to find the angle from F1. Is part of the problem. The question asks us to find the angle from F1. So it's just like way easier to draw the picture so that F1 looks more like this. I'm just going to make F1 be vertically downward. And then that makes the resultant look like this. All right. And so apparently F2's got to be, these are not to scale, okay? F2's up here somewhere, whatever. We're given that this is 90 degrees, all right? So, and again, this is the resultant, so it's R1, it's F1 plus F2. Now, what else am I given in this problem?
R is equal to F1, correct?
Right. We're also given that the magnitude of R is equal to F1. Also true. That's also given. What else? We're also actually given a value for F1 and for R. So it's for my problem, it's 1,280 newtons. Yours might be a little bit different, but different numbers, but same. 1,380 for me, rather. Okay, so what I'm supposed to do then, this is what's given. Once you sort it out. What's the question? The question that we're asked is, what is the magnitude of F2 and theta, where this is measured counterclockwise from F1. So I can draw theta here. All right. So how do we solve this one? By the way, this isn't really a F equals ma problem, is it? No. This one's kind of an oddball for this homework set. There's no motion or anything. It's just about static equilibrium, right? So
Is the resultant force equal to 1,380?
yes. I mean, if you want me to be a little bit more physical about this for a second, the stump is in, here's the stump, right? It's in static equilibrium. Actually, the stump has a reactant force of minus r this way, right? This is the stump. That's the force that the stump has put on the ground to oppose the pulling force of the horses, right? So the sum of the vector sum of the stump force plus F1 plus F2 has to be 0, right? In other words, minus R plus F1 plus F2 has to be 0, right? Of course it is because, well, all right. But anyway, that doesn't help us solve the problem. I'm just saying this is relevant to the lab we're doing with the force table, with the forces balancing. We on the one hand calculate resultant for two forces pulling on strings, but then we also have to, the place where we put the weight to oppose the two forces is on the other side for the same reason. I'm gonna erase this. It's distracting. All right. So guys, what do you think?
Assuming the weight F2 and F1 into the components.
Yeah, I think that's a good idea. This one is, I don't think I need to do trigonometry here necessarily, because if we just let F2 be like two things we don't know, let's say A and B, right? So we have what? We've got F1 is equal to what? 1380. Oh, I'm sorry. 0, right? Minus 1380. So here I'm assuming the usual thing. This is the y direction, right? This is the x direction. Okay? So with the usual standard Cartesian coordinates, F1 is this, and what's R? Right, I mean, these are both with newtons. Then what? Solve for F2, right? F2 is equal to what? I can solve this for it, right? F2 is R minus F1, which is 1380 newtons, comma 0, minus 0, comma minus 1380 newtons, which is 1380, 1380, and there's a newton. So there's the Cartesian form of F2, right? So you can see from that immediately that the magnitude of F2 is the square root of 2 times 1380 newtons, and that theta is 135 degrees. So that's 1950 newtons, roughly speaking, for me. How did I do that? Nothing too mysterious here. I'm just saying the length of this vector is the square root of 13, this squared plus that squared, but that's just twice 1380, right? Or if you don't like that, this we could rewrite as 1380 times what? 1, 1, right? So the length of this vector is 1380 newtons times the length of this vector. The length of that vector is clearly square root of 2. Anyway, you calculate the length of the vector however you want. How did I know that was 135 degrees? Well, that's 45 degrees, right? So got 45 this way, and then another 90 down here, 135. All right. Let's talk about the force of friction. And the normal force. So the normal force is a contact force. It is what it sounds like. It's normal to the surface, all right? So like right now I'm standing on the floor, right? And the floor is pushing back on me, right? So I'm putting the force of gravity, mg, down, right? The floor is pushing back up, right? With mg the opposite way. So the normal force from the floor is also mg directed upwards. The normal force doesn't have to be mg. It can be a lot of other things. But it is the necessary force to keep you from accelerating off the surface, all right? Force of friction, well, there's two kinds of friction. There's kinetic friction and there's static friction. Kinetic, static. So the kinetic force of friction is equal to the kinetic coefficient mu k times the normal force. In other words, it's constant, you know, for a given normal force. It is an unfortunate reality that we use N for Newton and we use N for normal force. These are not the same thing. It should be usually clear from the context which is meant. If this is troubling to you, you are free to use other notation. For example, you could, instead of using N, you could use F sub N for normal. Or, I don't know, maybe you have a friend who's especially normal, like Bob. You could say mu sub k times Bob, and that would remind you that it's the normal force. I don't know, whatever you know, you use whatever notation you want. I only have one rule, and that is that you cannot use a number as a variable. All right. I had a student last semester who kept trying to make 7 a variable. It was very annoying. His name is Joe.
What do you want it to represent?
It's a variable. It could represent lots of things, but I am not participating in his madness. I'm going to go on. So the force of friction static is less than or equal to mu sub s times the normal force. So this is an adjustable thing. It can go from 0 all the way up to some maximum value. Let me illustrate. So, static force of friction. Yeah. As you can see, this chair is putting a certain force on my finger backwards, right? That's coming from friction. If I just barely touch the chair, it's still putting a force back on my finger. That's from the force of static force of friction of the chair on the floor. But it's almost 0, right? And then there's some kind of critical, oh man, then we don't even cover that in here. That's a problem for statics. I don't even know what to do about that. That's torque and force all at once. Curses, I need a better example. There. So, see, but past a certain critical level, all of a sudden it starts moving, right? And actually, if you've done this, you'll have noticed that it's harder to get the thing moving, right? But once it starts moving, it's easier to keep moving, right? You break some sort of static weld between the two materials. So it's typically the case that the coefficient, this mu sub s is typically larger, is typically greater than the mu sub k. So the the max force of static friction is usually larger than the steady force of kinetic friction. And you could draw a graph to try to illustrate this idea. So it's a little bit complicated. If you just have something sitting on a surface with friction, is it going to move? Is it not going to move for a given force? Let me just give you an example of how this goes. So suppose that mu sub k is equal to 0.3 and the coefficient of static friction is 0.5, right? You've got a box, weighs, let's say, let's not say weighs, let's say that you have a 10 kilogram box. All right, so here's the picture. And I'm going to put a force on that box, all right? Like this. So here's my M. Then the question is, does the box move? Right? Then the answer is, I don't know. Without knowing about what the value of the force is, I can't say, right? So here's a few cases. Well, let me, forget that. So what's the free body diagram here? There's more at play now. So let me draw it down here. Yeah, I've got the force, the pushing force, F. The external force of, like I was pushing on the chair like that. The normal force is perpendicular to the surface. Whatever is required to keep the box from accelerating off or into the surface is what the normal force is needed to be. Of course, I also have gravity. mg like that. And then what else do you have? Which direction does the friction force point? Yeah, it'd be really weird if the force of friction pointed towards me, wouldn't it? Like if the force of friction pushed the box along, like made it go faster. Like, no, that's not how it works, right? So force of friction should slow stuff down, unless you've got some like really novel material. So here's the force of friction over here. That could be static, it could be kinetic. It depends on the force. Now, check out the acceleration here. So the acceleration, the acceleration is what? It's really a0, right? In other words, it's not accelerating in the y direction. It's staying on that level plane, right? So when I look at the equation, the net force is equal to mass times acceleration, I get two components here. I get the x component and I get the y component. Right? What's the x component say? The x component of this equation says I'm going to write the ma on the other side. I hope I don't blow your mind with that. So ma equals to what? What are the forces in the x direction? The pushing force, F, right? Minus the force of friction, right? And then how about the other thing? What's the acceleration in the y direction? 0. M times 0 is still 0. So 0 is equal to n minus mg. Now, in this case, the normal force is equal to mg. I again caution you, thou shalt not assume the normal force is always equal to mg. You have to think through it. There are other examples where that's not the case. All I have to do in this example is put the force at an angle, and the normal force is no longer mg. If this force has a little bit of a downward push or an upward push, that tinkers with the normal force. But there you go. Now, so then n is equal to mg, right? So what we got? We have ma is equal to the force minus mu mg. Right? Because in this case, the normal force is equal to mg, the nicest, simplest thing. So this will stay motionless up to what? So in the static case, what do we have? Static case. We have 0, right, is equal to the force minus 0.5. Well, I really shouldn't say 0.5. I should say mu times mg. What's mg? 98, right? So this mu is a variable. It can go anywhere. It's something in the interval from 0 to 0.5, right? It's a constant somewhere in there, in that interval. Let's go through some cases. If the force is 0, it just sits there, right? If the force is like, let's see, suppose the force was equal to 30 newtons. Well, this is worthless. What if the force was 30 newtons? What would the force of friction be in that case? It would be 30 newtons, okay? Can you get, because it's 30 newtons, so my question is, what is the, let me get to the point here. I've worked myself into a corner. It's my own stupid fault. But the static force, I always have a hard time communicating this because there's a lot of possibilities. But the static force of friction is mu, well, it's less than or equal to mu sub s mg. So basically 0 is less than or equal to the force of friction, is less than or equal to, in this case, 0.5 times, it's 49 newtons for our example. The maximum static force of friction that can be supplied by this particular interface, right, given the weight of this box being 98 newtons, is just a half that weight. Are we clear? Once you get past that magic number of 49 newtons, it starts moving. And then you're in the kinetic regime. Once you're in the kinetic regime, once you know that you're in the kinetic case, it's easier to think about. In the kinetic case, what's the force of friction? What's that? Yeah, it's just constant, right? It doesn't, so I mean, the static is adjustable. It adjusts to whatever it needs to be to keep it in static equilibrium, up to the maximum amount it can, as governed by the coefficient mu sub s. The kinetic case, it's just the coefficient times the normal force in this particular example. The normal force is just mg, right? So this is 0.3 times the normal force, which was 98 newtons in this case. So that would give us what? 29.4. Okay. So if you think about this process, what happens once you break the static weld, you've got an excess force, right? You've got a net force on it, so it's going to start accelerating. And if you think about pushing stuff and starting it from moving, you've experienced this, right? This phenomena that once it breaks loose, you get like a little push once it breaks loose, right? You don't have to apply more force for it to start moving. It's just already starting to move once that static weld has been broken. So, for example, if I push with, say, 100 newtons, right? So if F is equal to 100 newtons, then what we would have is mass times acceleration is equal to 100 newtons minus 29.4 4 newtons, so would have a net force of 70.6 newtons, and you could find that the acceleration was 70.6 newtons divided by the mass, which was what? 10 kilograms. So lo and behold, you'd have 7.06 meters per second squared as an acceleration, as an example, if your force was larger than that critical braking static force. All right. How does adding friction change the two box problem? What if I add friction to this problem? How is it different? I still have contact forces, right? And this is still very boring in terms of normal force, right? Because like I got, if you think about M1, I've got N1 acting up, I've got M1G acting down, I've got this contact force going that way, I've got the, oh I'm sorry, other way, duh. This is the pushing force. Contact force goes that way. And where does the force of friction go? Let's assume that we're in the kinetic case. Keep it interesting here. So if it's moving, force of friction goes which way? Right this way. And that's the force of friction for M1, right? And then there's also a free body diagram for M2. This time it's a little bit more exciting. On the one hand, you've got the normal force on N2 acting up. You've got the force of gravity, M2G, acting down. Those are equal and opposite because the y acceleration of the system is 0. It's not it's not going into the plane. It's not going off the plane. The acceleration vertically is 0. That means the forces in the vertical direction have to balance out. You're in static equilibrium in the vertical sense. And then you got the contact force like this, but what else do you have? Friction force to the left, right. And so there you're off to the races. I mean, so basically the vertical just gives us that N1 is equal to M1G. Over here you get N2 is equal to M2G. And then we just go back and do the same thing we did before. So like M1A, what's Newton's second law in the first mass? Well, I've got my force, pushing, and then what? I'm subtracting the contact force, and I'm also subtracting minus mu M1G, because that's the force of friction. Now M2, what's the deal? No direct pushing force this time, but we do have the contact force, right? And then minus mu M2G. And you can still find the acceleration much as we did last time. Subtract the equations, and what do you get? We get M1 plus M2. I mean, add the equations, I'm an idiot. M1 plus M2. A is equal to F minus mu M1G minus mu M2G. So this gives us that the acceleration, in fact, is equal to the force divided by M1 plus M2 minus mu G times the quotient of M1 plus M2